That sucked.
Yeah.
I actually didn't get that split for me, surprisingly. I just never survived.
Let's do this. Welcome. We are going to talk about explosion welding today. As you can see, here's a little sneak peek into what we're going to talk about. What is explosion welding? Explosion welding is a solid-state process that uses controlled explosive detonation to join two metals without melting them. A flyer plate of one metal is propelled into a base plate of another metal at an extremely high velocity, forming a bond through pressure and jetting. This is distinct from fusion welding, which is more commonly known because it preserves the properties of each metal that is used in the reaction, which is crucial for joining the dissimilar metals and keeping the properties. The objectives today are to provide a detailed overview of what explosion welding, how it works from choosing the materials to the final product, analyze the advantages and challenges of the process, explore technological advancements, and reflect on what our team has learned through this process. Why does it matter? It is widely used in high-tech industries such as aerospace, naval, and chemical processing, where combining materials of different key thermal properties is necessary. Because no melting occurs, this is ideal for metals that would distort or degrade under high pressures or heat. It is also cost-effective using in large-scale systems.
So the process and methodology, the most expensive part of this process is the initial research and calculation to determine the material and explosives, whether you're looking for thermal conductivity properties, electrical conductivity, or something along those lines, and then looking into the research of the material for the explosive, how fast you need to explode it, its duration of the explosion. So that's the most expensive part. And then they have to select and clean the base and flyer plates off of that research, position them with a precise gap using standoff devices, and then placing a controlled explosive layer over the flyer plate, and then you press the button and you explode them together. So technicalities. So the standoff distance is the gap between the flyer plate and the base plate, and if it's too small, like in this area, all you'll get is waves, and then if it's too large, you'll get heat-affected zones right here where the two waves would meet. The detonation velocity, the speed at which the explosive wave, you want to make sure that's even and constant throughout the entire process. The flyer plate thickness balances strength and flexibility. If it's too thin, you'll get ripples like in the top left, and then if it's too thick, you'll have poor bonding where the material won't be able to form enough to bond together. Collision velocity must be high enough to bond the metals but not cause damage. Key part of explosion welding is there's no heat affected zone. If it's too hot or if it's too high of a collision velocity, it'll create too much heat, ruining the bond. The weld angle, which will affect the wave patterns, and jetting. And then jetting is the self-cleaning effect during collision. So it removes all of the surface debris like scale, any oxidation, stuff like that on the material that was missed during cleaning. This jetting effect cleans that off, and if the velocity or anything else is off, we will not get that jetting effect.
Circling back to where it is widely used, especially in aerospace, naval, and chemical processing, some of the common flyer plate materials are titanium and base plate as stainless steel, copper, and aluminum. Here's a chart here of the most common metals used and their properties and applications, and if they're used as a base or a flyer plate. The most important properties are strength, corrosion resistance, ductility, and thermal conductivity, which will be combined properties of different metals, and obviously some real-world applications could be in some aerospace turbine parts or planes or jets.
So going into the advantages, one of the biggest advantages with this is you can combine two dissimilar metals. So in this picture on the bottom right, you can see that there's copper and aluminum joined together. So in this example, you can get the benefits of the conductivity from the copper along with the corrosion resistance of the aluminum. And so this is really good for sheet applications. So large sheets can be welded all together at once. And it doesn't require fillers, and there isn't as much porosity issues like other welding applications. And some of the limitations are just handling of the explosives. Not exactly just the process itself, but just in the work environment, you have to handle explosives. There's more regulation, and that drives up cost. There's a lot of post-processing often required because the metals cannot be too hard. If they're above a certain hardness, the process will not work. So often they need to use softer metals and then heat treat them or cold or hot work them later to get the correct mechanical properties that they need.
All right, moving on to the latest advances for explosion welding. Focusing on this slide on the finite element method. Basically what the finite element method is, it's especially for explosion welding, is simulating the process of explosion welding, so you're not really wasting your material when coming to explosion welding because it's a fast and sometimes, you know, not exactly the easiest to line up exactly where you want it. It's a lot easier if you're focusing on a simulation where you're like, oh, I can follow this and this is how it'll turn out, versus just kind of going into it a little bit blind. Yeah, so just optimize modeling of the effects of explosion welding, especially when it comes to different types of metals. Moving on to crystal twinning and automotive production. Crystal twinning is basically when the lattice structures of the two different metals line up. Why this is super helpful is it increases the bond strength between the metals. And a little research has gone into this, trying to optimize the explosion welding to better line up so the bonds are better and stronger. And then especially in the automotive production, explosion welding is being used and tested to give car body strength and the strength of the traditional steel bodies with the lightweight properties of aluminum. And then moving on to welding in a vacuum. Basically, because explosion welding is such a loud process, of course, you're using explosives. You have two sheets pounding together at high velocities to form those bonds, and controlling that combination. It's not exactly the quietest thing in the world, which means you can't really use it in residential spaces as much in manufacturing plants. But what solves this is putting it in a vacuum, which would effectively take away the sound pollution that it would create. And lastly, you would be, actually able to incorporate it in more residential areas.
So just an overview on the future outlook of this technology. One of the biggest things is just the new up-and-coming research on finite element analysis with explosion welding. So what's nice about the FEA is that you can test like hundreds of different alloys, and you don't actually have to physically do the test. You can have it do a simulation to test out different bonds, to test out different weld strength characteristics, and then back to the twinning, twining. So this is another big future outlook for the automotive industry especially.
So for our team reflections, explosion welding is a very niche process. It's not applicable everywhere. It's kind of needed in a special case, especially in the military and aerospace. So that's one thing that we learned. Key benefit of explosion welding is its ability to join two dissimilar metals. So you may have a metalloid and a metal alloy, or some sort of combination where you're looking for both of the properties to be in one single material. The operators of these processing machines are highly specialized, so this is a very skilled trade, kind of similar to welding. So you're joining two materials together, have to be very strict in how that's done and how well trained the employees are. And then continue to research in these areas could streamline and optimize setup procedures. It's a big thing. It's a single process, so it's kind of hard to daisy chain multiple processes together. So kind of looking into innovation on that side to kind of streamline this and make it more applicable to other industries. These are sources. Thank you. Any questions?
So what's the status of commercialization of this technology? Any companies out there, or is it still in the Army system?
Most of it is Army, just because it's contract-based. So you need a lot of research and you need a lot of money to go into that research. So that's where that comes. Once that research is and since it is contract-based, I don't know personally if it's public information. I haven't been able to see anything, but if that information ever becomes public, then other industries can kind of take that over and hopefully streamline it and do that.
I think also the explosives that they use might be only available to some industries, like the high trade of like military, but there is a lot of research actually out there about the different types of metals that you can bond together and like what their properties are, but not exactly about like the machines they use or I guess what materials, but more of just like what comes out of the explosion molding.
So are the studies mainly in the U.S. or it's a kind of a worldwide study? How about the literature?
I think it's
What's found is mainly US.
Yeah. I think we have the most research and development towards it. I'm sure other militaries use it. Obviously, there's definitely classified information elsewhere.
Okay, that's my question. Any other questions?
Do you see like research on, so all the presentations about like large scale like things, any like research on like a nano or micron level, like a thin sheet of material using those two binding together?
Nothing on that side I haven't seen personally, but I will say, like, going back to this slide, this is as small as we can see, is just the bond layer. I personally don't know, I mean, it says 500 micrometers, is that what that is?
Yeah.
Nanometers? So you need a relatively thick piece of material to even get that kind of wavy pattern and where it bonds together. So I don't know how applicable a thin sheet of metal would work in this.
Yeah, because you don't want to deform the metal also when you're doing explosion welding, so it doesn't.
And yeah, another question is like when you're choosing, so like the flyer plate and the base plate, right? So when you're choosing those kind of, if you're given two materials, is there any like rule of thumb? You can decide which one should be the base plate, which one should be the flyer.
I think that, I guess, so we're seeing, let's use these two for example, the steel and titanium. I think like since the steel would be the base plate, it would go like maybe on the inside of the material to hold for stability and like, I guess it could be cost effective as well, but the titanium could be from the outside. You see how it says the common applications, aerospace and like medical, corrosion resistance, so anything exposed to the air would be on the outside. So I guess it depends what you want. But I don't know,
I don't see why it would matter.
yeah, it's kind of just what you're looking for, right? But
Yeah, I'm thinking of maybe like related to like the ductility or like the mechanical strengths for some of them, like when they are under like this like high velocity.
Like you're worried about like for example, if the bottom metal was more dense, it would be better for like the top metal or whatever to be less.
Yeah, I'm thinking of
or
that
something
way.
like that.
I'm trying to see if you have see anything like about that when you're choosing like.
oh, like
bonding.
exactly what you're gonna make out of the two materials? Is that what you're
Yes,
saying?
for example, if you want to bind into materials, for example, aluminum with like copper, so which one should be the basic one, or which one should be like the flyer one? Which one should be on the top?
Some of them are pretty, like, you see the copper and the aluminum are prety, is that what you're asking right here?
Yeah,
like,
but I just make an example, not specifically like which two
Yeah.
materials. Like, are they, for example, if I have two new materials and I don't know anything, they don't do any preliminary test,
Yeah.
but based on like some kind of experience.
So you're saying, is it better to have the copper on the bottom versus aluminum on the top?
Yeah,
and
for
then
example,
flip?
if I have a material which is like have a higher hardness, and another one is like
Yeah,
lower.
from what I saw, they're not always the same sheet thickness as well.
Yeah.
Sometimes like the thinner sheet, for example, it might be like aluminum on steel or something like that, is usually on top.
So it's basically like.
So it has something to do with the ductility and also the thickness. Yeah.
Okay, yeah, thank you. Because I didn't read those kind of things. Just want to know like if I want to do something similar, which part should be on the top, which one should be the.
Well, if you're using it for say like an airplane for like the military like space, if you're flying something where the heat on the outside like you know, any of the fighter jets or something like that, where there's gonna be a ton of stress on the outside of the plane, I think, or I would assume you'd use something that's a higher hardness and strength, like titanium, where you need the, you know, something just on the inside to act as a barrier, but you wanna save money. I think you'd use something as steel or aluminum that's a little bit lighter weight than titanium. So I think in an application like that, you would have the titanium on the outside,
Yes.
and then the steel on the inside, and then the thickness of that would really depend on, you know, all the research you put into it.
The structures or finding out the method or simulations or anything like that, depending on where you're actually having the explosion.
Yes. Okay, thank you.
Yeah. Thank you.
Yeah, good job.
Thank you.